Hey everybody, I'm going to go over kind of the mechanistic patterns that we're going to see throughout this class. So we're going to start with 3 of them, and then there's going to be another one that we'll bring up probably next week. But I think having the reactions for that one will actually be helpful in that instance. So we're going to save rearrangements for a little bit later. So for right now, we're going to focus on the first 3, which is nucleophilic attack, loss of a leaving group, and then proton transfer, which is the acid-base reactions that we've been working on for a while. So for nucleophilic attack, what we want to be looking for is we're going to have 2 parts of our reaction. Okay, so we're going to have minus and a plus. Okay, so the nucleophile is going to be the negative part. It's the part that's electron rich. The positive part is going to be the electron poor part. So when we're looking at this, if we look at something like a carbocation, obviously very electron poor. And then let's say we just have an alcohol. Okay, the 2 pieces here, the carbocation is our electrophile, as in something that likes electrons and wants electrons. And then our alcohol is going to be our nucleophile. Okay, and when we're looking at where our electron density is actually coming from, it's coming from that oxygen lone pair. Okay, so with this lone pair is going to come and make a bond to that positively charged carbon. I'm actually going to move this over here so that I can make my arrow look a little bit better. Okay, so we're essentially going to be sharing that lone pair between the oxygen and this carbon. Okay, so we're making a new CO bond. So we want to make sure that anything that I don't have arrows to, so namely that H and the methyl over here, those do not leave. They are still present, and the other lone pair is still present. Okay, and now that oxygen is positively charged because we're sharing electrons that it didn't really want to share in the first place. Okay, so that is an example of a nucleophilic attack. You've got your nucleophile, you're going and attacking your electrophile and forming some kind of bond. Okay, so where this is our new CO bond. Using the oxygen lone pair. Okay, so that's where the electrons come from to actually form that new bond. All right, so let's look at another example. So if we have, let's say we've got an ester. Okay, and then we add in some sort of hydroxide. So this could be sodium hydroxide, potassium hydroxide, whatever you want. So if we have these 2 pieces, I think it's fairly easy to see which one is our nucleophile because we've got a negative charge on it, right? So nucleophiles are going to be negative. We've got electron rich, okay, types of compounds. So this is electron rich. So this is our electrophile. Okay, so we've got electrophile here, nucleophile here. And if we're trying to figure out where on our electrophile we actually have something that's electron poor, we want to really be thinking about this resonance structure where you can put a delta plus on that carbon down there. Okay, I should have given myself space to do that. Okay, so if I have this, right, that resonance structure right there is showing me why I have a delta plus on that carbon. So resonance structures can be really, really helpful in helping us see where the reactive parts on a molecule are. And then you can see, oh yeah, that carbon is electron poor. So I can use that as an electrophile, okay? So we're just gonna box that. Okay, and I'm gonna erase that one. Okay, so when I'm having my nucleophile attack this electrophile, so let's take that attack right there. So when I was up here, when I had that positive charge, I only needed to do 1 arrow because this carbon is positively charged, so it still needs 4 bonds. So I was just able to give it that 4th bond without moving anything else. this carbon already has 4 bonds. Okay, so it's only a delta plus, it's not a full plus. So in that case, something has to be moving on this carbon in order for me to actually form this new CO bond here. Okay, so what that's going to be doing is we're essentially going to be moving the same electrons up onto the oxygen that we did for this resonance structure. So if you want, you can even say that, right? You can just attack your resonance structure directly. But you have to have the 2 arrows, one showing the nucleophilic attack, and then one showing that lone pair being moved up onto the oxygen so that you don't break your octet on your carbon. Okay, so now we have an O minus up here. We've got an O with a methyl, and we've got an O with an H. Okay, so then we end up with that intermediate. So we broke the pi bond, and we've got a new CO bond. Okay, so our second pattern is going to be the loss of a leaving group. Okay, so leaving groups are really important in terms of just kind of making space on an atom for a reaction to occur. Okay, so if I have this compound, this is tert-butyl bromide. The bromide, just remember, if we think back to kind of acid-base chemistry, Br minus is a very stable conjugate base. Okay, it's a very stable anion. So if I want this bromine to just leave, it can. There's nothing stopping it from just leaving. Okay, so I can just kick off that bromine, and that's going to give me 2 separate pieces. One's a carbocation, and one is my Br minus. Okay, so things that can be leaving groups have to be stable as the leaving group. Okay, and it's easy to think about kind of in terms of acidity, right? If we're looking at this as a conjugate base, it's a very stable conjugate base. HBr is a very acidic acid. Okay, so we've got our leaving group right here. I'll often abbreviate that as Lg. And so we're just having our leaving group leave. It's going to take electrons with it, leaving behind a positive charge. Okay, and there are some instances where we'll see leaving groups get pushed off by other things. So an example of that, just move this down a little bit, would be something like this. If we had an O minus here, a Cl there, and an OH. Okay, so if we're thinking about that, if we're looking at this, carbon does not want to be negative. Okay, carbon and hydrogen, you will not see them as leaving groups just as they are. So carbon and hydrogen never leaving groups. But if we look at chlorine or oxygen, those are both electronegative atoms. We know that in a lot of cases that holds the negative charge quite well. But between the 2 of them, which one would be best, right? So is HCl a stronger acid, or is H2O a stronger acid? So hopefully when you say that to yourself, you think, oh, well, HCl, obviously, because we've got a much bigger atom. So in the case of chlorine versus an OH, Cl minus is much more stable. Okay, so the Cl is going to be our leaving group. And we're actually going to push it off by the reformation of a pi bond here. So we're going to form a pi bond, and at the same time, that's going to kick off that chlorine atom. So now I formed myself a carboxylic acid and Cl minus. Okay, so again, it's a stable leaving group, it's a stable anion. Oftentimes you'll also see stuff like water be a leaving group. So if you have something that's protonated, so let's do one other example here. Okay, so if we have something like this, that is going to be a good leaving group because water is a very stable molecule, right? Okay, so if we just kick that off, again, this is going to get us to a tert-butyl carbocation and water. Okay, so again, we've got our leaving group right here. And then we have it over here. Okay, so leaving group, leaving is another pattern. Okay, then our final pattern is proton transfer chemistry, so like acid-base chemistry. So if I start with this with a ketone and I add in HCl, okay, this is something that hopefully is familiar at this point. At this point, we should be thinking about, what's our basic atom, what's our acidic atom, or what's our acidic proton. So we can say, oh yeah, this oxygen has lone pairs. That H on the HCl is quite acidic. So we can go protonate the oxygen. We're going to kick off the chlorine. And we're going to end up with our protonated ketone and chloride as our conjugate base. Okay. We've also seen other instances where we have something like a phenol. Let's react that with OH minus. Okay. We can have that lone pair attack that H, give electrons to the oxygen. Get that as our conjugate base and water as our conjugate acid. Okay. And if you look at this, the proton transfer stuff, the leaving group stuff, all of that is just down to kind of thinking about what's positive and what's negative, okay? Or what would like to be negative. So in this case, that oxygen is more electron rich, okay? This hydrogen is very electron poor because the chlorine is hogging all those electrons, right? So this H is electron poor. This OH minus is electron rich. So we need to start practicing kind of viewing where our electron density is, and areas of high electron density are going to react with areas of low electron density. And that covers about 95% of organic chemistry if we just kind of keep that thought in mind. So let's go ahead and look at an example here. So this is a mechanism showing the hydrolysis of an imine. So this functional group right here is an imine. This is chemistry that we will dive deep into in the second semester of organic chemistry, but it's really, really helpful in terms of identifying kind of the patterns that we're going to see in these mechanisms. So even though we're not going to learn this reaction, we can still kind of go through it and see how would I draw the arrows to get from this one to this one. And then what are those parts actually in terms of patterns, okay? So in this first step, I'm looking at this imine, and then in the second step, it has a proton on it, okay? It got protonated. This is an acid-base reaction, okay, or proton transfer. I don't really care which one you call it. It doesn't matter to me. So the way that that's going to happen, I'm going to use my nitrogen as my basic atom, and then my hydronium is my acid, okay? So we're going to use the nitrogen lone pair to go make a bond to the H, and then that bond will give the electrons to the O. And I'm going to do these in a different color, sorry. Okay, so we have that happening. So now we've got our conjugate acid and we have water. Okay, so water is our conjugate base. The protonated imine, which is now an iminium ion, is our conjugate acid. So now it's saying we're adding the water in, okay? So the water is going to do a nucleophilic attack. Okay, we've got something with electron density. This carbon is electron poor because this nitrogen is pulling electrons towards it. So the water here is going to go attack that carbon. But if we look at this next piece, there is no pi bond here anymore. And that is because we had to push that pi bond up onto the nitrogen as a lone pair, okay? Because otherwise we'd be expanding the octet on that carbon. That's a no-no. All right, so we did our nucleophilic attack. Now we've got this piece, which is protonated. So we've got essentially a protonated water. And if we look at the next step, what's changing, we're taking away a proton. Okay, that's another acid-base reaction. In this case, we're going to use water as our base. We're going to go grab one of the H's here, give the electrons to our oxygen there, and now we're back to a neutral molecule again. Okay, but then it says, oh wait, we're not done. We're going to bring in the hydronium again and then protonate our nitrogen. So another acid base. We're going to use the nitrogen lone pair, grab that H, give electrons to the O, and we get to our, now nitrogen is protonated. And now, what the heck is going on from these two? Okay, so when we are at a position like this where it is hard to see what's going on, I would recommend numbering things out, okay? I'm gonna start saying this over and over again, number your carbons. So I'm gonna start with this carbon here, 1, 2, 3, 4, 5, 6, 7, 8, 9, and nitrogen's gonna be 10. Okay, and then I'm just gonna say the oxygen is 11. Okay, so if I'm looking at this, I think I can pretty safely say what my nitrogen is. That's gonna be 10. And I think I can probably safely say my oxygen is 11. Oops. Okay, so if I have these two, if I'm looking at this, the nitrogen is connected to a CH2 over here, carbon 9. That probably has not changed. Okay, so this is probably 9, oops. 9, 8, 7, 6. Okay, so that just looks like this whole piece kind of opened up, right? And then 6 connected to 5, 4, 3, 2, 1. And I have that 1,6 bond still intact, okay? But the bond that broke is the 1 to 10 bond. Okay, so we're looking at this guy right here. So that bond broke. And I made a new pi bond between 1 and 11. Okay, so if we add all that up, I'm going to zoom in a little bit so we can see it a little better. So what that's going to mean is that if I'm looking at this oxygen, it's positive here, but neutral here. So I'm using one of these lone pairs to go make a pi bond. Actually, boy, I did not do myself favors with my number placement. Okay, so we're going to use the lone pair to make a pi bond here between 11 and 1. So that's that one checked. And then since I have to have some sort of space made up on carbon 1, this is going to have to leave. Okay, so this is essentially a leaving group step. Okay, anytime that we're making space for another atom or something is coming off, that's going to be our leaving group. Okay, so this whole group here is the leaving group. And it's a stable leaving group because it's a neutral molecule once it's gone, right? It opens up, the nitrogen is now neutral, it's not positively charged anymore. It's in a much better place. Okay, so then that's going to have us open this whole thing up that way to get to this product. So now our final step, if we're looking at this to this, most of that all looks good. We just have this is positive and then it's neutral. So we're going to do another proton transfer step. and then we get to our final product. And then what's not listed here is you made hydronium again. Okay, so it's catalytic with the acid. So as always, let me know if you have any questions. We will be practicing this for a whole year. So please let me know if you have any questions, and have a good one.